Alright, so today we're basically just going to be going over various problems involving limits to continue building intuition and find out how to solve different types of problems. Let's just get started. Alright, limit as x tends to infinity of cos x over 3 divided by log base 2 of x. So we know that the cosine function just oscillates between -1 and 1, right? That's its range. And log base 2 of x as it goes to infinity is just going to be growing unbounded to some infinite number. So clearly what happens in this case is because the denominator is so large and the numerator is just going to be like a small value, it's going to go to 0, and that's our answer. Pretty simple, right? Alright, let's go to the next one. Limit as x tends to 1 from the right side, square root of 7x minus 7x squared. I think one way to go about this is we first factor the polynomial term inside, so we get more intuition about this problem. And this can be factored by taking the 7x out, and then we have minus 1 minus x, right? So clearly, we see that the range of the domain of this function, if you sort of graph it out, right? This function, or like the inner part right here, this part, is negative when x is greater than 1 or less than 0, or oops, I drew this wrong. But whenever x is greater than 1 or less than 0, our function will be sort of negative, right? And so if we're coming in from the right side, we're gonna have some negative value over here, and we can't take the square root of a negative number, so this just does not exist. Right, because if we come in from the right side, this is going to be the same thing as the square root of 7 times 1 from the right, and then some negative value. I'll just put a minus sign here, and that will give us a negative term, and we can't really do that because we can't take the square root of a negative number, so that limit from the right hand side just doesn't exist. Alright, number 3. Limit as x tends to 8, x to the 2 over 3 minus 4 divided by x minus 8. Now, if we try to plug in 8, we clearly have a problem, right? Our denominator is not really defined at 8 because we'll get a 0. What can we do? This top part right here sort of looks like the difference of squares, and in fact it is. So let's try to, we can do x to 1/3 minus 2 times x to the 1/3 plus 2. Let me box this, by the way. Divided by x minus 8. What else can we do now? Well, we know that 8 is just 2 to the power of 3, right? And so this can be noticed as the difference of 2 cubes. And so we can factor the denominator as well. So this is just limit as x tends to 8 of x to the 1/3 minus 2 x to the 1/3 plus 2 divided by, if we know the formula for the difference of cubes, we have x to the 1/3 minus 2, and then this one's just x to the 2/3 plus 2 x to the 1/3, right? Because this is 2 to the power of 1, and then this x to the 1/3 to the power of 1, and then plus 4. And very nicely, this term cancels out, and now we can plug in 8 into whatever's left over, and we get 2 plus 2 divided by 8 to the power of 2/3 is 4, plus 2 times 2 is 4 plus 4. So we get 4 over 12, which is 1/3. So I mean, clearly you saw how the last problem is pretty complex, but when we have limits, a lot of times factoring sort of helps us, and that gives us a final answer, 1/3. Alright, let's go to the next set of problems. Alright, so I think this is number 4. Limit as x tends to pi over 6 secant 3x divided by tan 3x. One thing is whenever we have these secant tan functions, we know we can write it in terms of cos and sine, right? So I mean, that's what I'm going to try to do. Probably will simplify something. Secant is just 1 over cosine, so 1 over cosine 3x. And then we know that tan is sine 3x divided by cosine 3x. And look, we have terms that sort of cancel it out, right? Because this is basically the same thing as limit as x tends to pi over 6 of 1 over cosine 3x times cosine 3x divided by sine 3x. And this cancels out. So this is just the same thing as limit as x tends to pi over 6 of 1 over sine 3x, which is equal to 1 over sine 3 pi by 6, which is just pi over 2, which is just 1 over 1. And that gives you your final answer of 1. Alright, number 5. Alright, this might look daunting at first, but I promise you, it's not too bad. Limit as x tends to infinity, so we're dealing with limits as you go towards infinity, of 4x squared minus 6x minus 2 all over the square root of 9x to the power 4 plus 3x plus 5x cubed. Alright, so whenever we're dealing with infinity, we sort of want to see what grows faster, right? Is the numerator growing faster, or is there denominator growing faster? And whenever you have that, the term with the highest power sort of rules it out. So that's all we care about. And in this case, when we take stuff out of the square root, right, this term has the highest power, so that's all that really matters. The rest doesn't really do much, because the rate of growth of x to the power 4 is much higher than the rest. So we can simplify this sort of just doing limit as x tends to infinity of 4x squared, right? And then we can ignore the rest. We'll just call it like some y, right? Some constant. And then if we were to take out like the leading term, the x to the power 4 term, right, we'll get like some 3 to the power of x squared. And then minus some like z, right? And so this is the only part we really care about. And we see that if we were to divide out the x squares, we'll just be left over with 4 over 3. And that's our answer. Alright. So, number 6. Limit as x tends to 2.99 from the right hand side of the floor function 2x divided by x. Alright. So here, I mean, there's nothing special. I mean, I guess the problem just tries to scare you because it has a floor function, but I mean, at the end of the day, we can just plug it in, right? This is one of the simple problems. So 2 times 2.99, I think it's 5.98. And the floor of that is just simply 5, and our denominator is 2.99. So that's equal to 5 over 2.99, or 500 over 299. Alright. Number 7. limit as x tends to 0 from the left-hand side of square root of 4 plus the square root of 4 plus x over x. We clearly see if we try to plug in 0, I mean, our denominator is going to give us 0, and that's going to lead to problems. So how do we go about this? Well, one sort of way is it's a left-hand limit, so let's just do 2 plus 2 over 0 from the left side, and that is like 4 over some negative value, right? Because we're going to 0 from the left side, so this is negative infinity. There's no other way of like sort of simplifying this because 0 is going to be a problem. Alright. I think we're on number 8. Limit as x tends to negative infinity of 3x, 3 to the power of x times x cubed divided by 12 to the power of x. Here we clearly see we are dealing with exponentials, and that sort of grows faster than everything else, so that we can say equals the limit as x tends to negative infinity 1 over 4 to the power of x times x cubed. 1 over 4 to the power of x is an exponentially decaying function, right? Especially if you go towards infinity. But whereas you go to negative infinity, this grows. And because this, when you have negative x to the power of 3, that'll give you some negative value, right? So this is sort of like, this is going to be infinity times like some negative infinity value, so it's just negative infinity. Alright. Number 9. Limit as x tends to 0, secant x divided by 2x. Now we can try to represent this with some familiar trig functions that are easy to manipulate. 1 over 2x times cos x. And if you plug in 0, we see we still have that denominator at 0. So we want to see here, in this case, if our limit sort of converges towards like 1 infinity when we go to 0 or not. So here we see the left and right side limits. So we try limit as x tends to 0 from like plus or minus, and then we look at 2 times like, 0 from plus or minus, and then cos 0 from plus or minus. We know that this term is just 1, right? This term, though, if we're heading from the positive side, it's going to be some positive value. But if we're heading from the negative side, we're going to get some negative value. So that implies that the limit as x tends to 0 from like the positive side, we're going to get some like small positive value. So it will just be like, positive infinity. Whereas the limit as x tends to 0 from the negative side, our denominator is going to have some small negative value. So that's going to get to negative infinity. And the left and right side limits are not the same. So this answer to this, the limit does not exist. Alright, limit as x tends to negative 1 from the positive side, x squared minus x minus 2. Can we factor this? I think we can. So let's do that. Makes your life much easier. This is just x minus 2 times x minus, or x plus 1 rather. So we clearly see is if we head to negative 1 from the positive side, we're going to get something like, this is going to be around negative 3, right? A little less than that. And then this is going to be some positive number. And again, this is not 0, but it's like some positive number that's a bit greater than 0. and that gives us like some small negative number. We can't take the square root of that, so that means that this limit also does not exist. Alright, let's go to the next set of problems. Now I forgot what number we are, so we'll just call this, I don't know, 3 again. And this should be very familiar, in fact, to a problem we did. -8. Clearly we can't plug in -8 again because x, or -8 to the 2/3 is just 4, and then we're going to get 0 in the denominator, and that's not something you want. But like that problem before, you can factor both the numerator and denominator, because the numerator is just a sum of a cube, so this can be represented as x to the power of 2/3, x to the power of 1/3 plus 2 times x to the power of 2/3 minus 2x to the power of 1/3 plus 4, and denominator is a difference of the squares, so that's just x to the power of 1/3 minus 2 times x to the power of 1/3 plus 2. This two terms cancel out, and now we can just plug in -8, and what we get is 4 minus, or plus 4 divided by minus 4, right? So that will just be positive 12 divided by minus 4, which gives us minus 3. Alright. Limit as x tends to -pi/6 from the positive side of cosecant 3x divided by cotangent 3x. Cosecant is 1/sine, so 1/sine 3x divided by cosine 3x over sine 3x. Now these two cancel out, and we're just given limit as x goes to -pi/6 from the positive side of 1/cosine 3x. If we were to plug in -pi/6, we get 1/cosine -pi/2, and from the plus side. So if we're going from the plus side, it's going to be a bit greater than -pi/2, right? And that means when you're a bit greater than -pi/2, well, first of all, cosine -pi/2 is just 0, and we want something that's a bit, or in terms of magnitude, let me rephrase. -pi/6 from the positive end, we're going to get some sort of value that is a bit greater than -pi/6, right? And in negative numbers, when you're greater than, that means your magnitude's a bit lesser. So that means our 3 times -pi/6, which leads to -pi/2, like we saw over here. That means whatever's in here is a bit greater than -pi/2. So if we're like in the unit circle right here, we're somewhere here, like some angle over here, right? And that means that this value right here is, we know that cosine is positive over here, right? So then this value is some small positive number. So that means 1 some small positive number just gives us infinity, and that's our answer to this limit. Alright, we're almost done. Let's go on to number 5. Limit as x tends to -infinity 3x plus 5x plus 2 divided by square root of 9x squared plus x minus 1. Again, we're dealing with limits towards infinity, so we only really care about like the most powerful term, right? Which function, which term leads the growth, right? So in the numerator, we have the highest degree is x, so its coefficient is 8. And in the denominator, when we take the square root, we'll get like some 3x and some other junk that we don't care about. And when we go towards infinity, what's going to be left over is just the coefficients, because these two cancel out. So it's 8 over 3. Oh shoot, we're going to negative infinity. Alright, when we're going to negative infinity, both of these terms are, well, the denominator is positive, right? But the numerator is not positive, so we're going to get negative 8 over 3. My bad. Alright. Number 6. Limit as x tends to 3.99 from the positive side of the floor of x over 2 divided by x. Again, here's just like a plug and chug sort of thing. There's nothing too special, right? So 3.99 divided by 2 is 1 point some term. We're taking the floor of that and divided by 3.99. So it's just going to be 1 over 3.99, which is equal to 100 over 399. Alright, a couple more problems. Limit as x tends to 0 from the left side of sine 3x whole squared divided by x squared. Here, I mean, we can't really do anything, so whenever we plug in 0, we're going to have to deal with some sort of infinite value. So the denominator is going to be some small positive value, because we're going from the left side of the negative end, but we're squaring it, so it's going to be some like positive small value. And sine x, sine of 0 is actually just it's just 0. Oh wait, hold up. This problem requires us to know that sine x over x gives us, well, the limit of z as x tends to 0 sine x over x is 1, right? So limit as x tends to 0 from the left side, we can sort of simplify this to, oh, this is squared, sine 3x over x times sine 3x over x. Now, we are told that the limit of sine x over x is 1. Nothing about like sine 3x over x, but we can still manipulate this in a way that will get us our answer. How so? Well, we know that this is the same as right? Sine 3x over 3x. And we know that the limit of sine, a value divided by that same value is 1. So that's just the same thing as 3 squared, and that gives us 9. And for a final problem, limit as x tends to negative infinity of 8 to the power of x divided by 16x to the power of x to the power of 4. We can rewrite this as limit as x tends to negative infinity of 1/2 to the power of x times 1 over x to the power of 4. We know that this term is going to lead to some infinite value, right? Because that's just how the exponential function works. And the second term is going to give us some positive value, but this grows faster than, this positive value. So we're still going to get a non-zero answer, and it's just going to be positive infinity. Alright, so that's basically it for the coverage of limits. We went over like a lot of different problems, a couple of strategies, couple of strategies. Well, we saw you can plug it in, right, whenever possible. If not, factor. We haven't seen a problem of the sort yet, but you can also multiply by conjugate. And finally, obviously that's not comprehensive, but I just remember like one-sided limits, you gotta sort of think about this as being like a small positive, small negative value depending on what happens, and that'll tell you like whether it's going to positive infinity or negative infinity.